So now, we're going to evaluate your limits algebraically. They should actually match what you did last night. But it gives you a better chance to see all the different ways we can approach a number. And we still write the limit to make it look like this. As x approaches 4, what is that number going to be? Sometimes the limit is there. Sometimes it's a point that's not there. If it's just a point, it's like filling it in on your graph, filling in a point of discontinuity. Yesterday, and you didn't see yesterday's, we looked at if it was a removable point, we can fill it in and make it continuous. Or if it's a jump, we can't, and it will not be continuous. So those are things we're going to look at. Now the first one is a nice one. The first one says, okay, direct substitution. The reason we can do a direct substitution, there are no domain restrictions. We have no denominator. We have nothing to worry about. So, but without a domain restriction, we just take 4 and we plug it in. Could we even just put it into your graph and take it off the table? Absolutely. But all we want to do is just substitute this in. So this will give us 16 plus 8, 24 minus 5. Our limit is 19. So as x approaches 4, that's the number. That's the point. 4, 19. It exists. It's there. 4, 19 up here somewhere. It exists. Your limit can be there. It still is the limit for that number. This one, I'm hoping you'll recognize this one, because this is the one that we had a point of discontinuity. When we graphed this was called our rational functions. We have a domain restriction. Your denominator cannot be 0. So when x is -3, your domain says, get -3 out of there. Remember doing this? We cannot use -3. But we want to know, and this is what you did last night, does your graph approach a y value from the left and from the right at -3? So last night you graphed it, you set your table to the thousands, and you notice, what would this number be for -3 if I could fill that in? -5. Now, what we did way back when we did rational functions, algebraically, we factored and reduced. So we're going to take this, we're going to factor the numerator. Then we can take out your common factor, and remember doing this? We said if we have a common factor, it's still a domain restriction, but when we're able to eliminate that same factor, we have a point of discontinuity. And we took the rest of this, we simplified it into just this. So we took your point of discontinuity, we set it equal to 0, we found your x, and then we took your simplified function, after you eliminated that factor, and we plugged in, now we can plug in that -3. So -3 minus 2 is -5. So here is your point of discontinuity. It's a removable point. So we can look at it in your graph, and we can look at it algebraically. Remember doing this when we did functions? Remember when we did your whole thing with increasing, decreasing? Good. Okay. Then we have a few more examples. We have this. And last night you looked at these graphically, and you can see where they would converge. It's a point of discontinuity. If I plug a 1 in here, this is going to give me 0. 1 minus 1 plus 1 minus 1. This is going to give me 0. This is my domain restriction. So technically, this point does not exist. So for me to see if we reach a limit at that, as we approach that point, algebraically, we're going to factor this out, and just like we did the last one, if we can eliminate a factor, that's our point of discontinuity. So when we factor, we're going to group this. What can I factor out of the first group? X squared, good. And what am I left with? Good. Which is this group. So I'm just going to factor out a 1. Take out your common factor, and then this is the factor that's left. So we're going to take this over this. Can we now eliminate a factor? X minus 1. Good. This is your point of discontinuity. So what's left in this is 1 over x squared plus 1. So we're going to take your point of discontinuity, just like we did in the last problem, and now we can substitute it into this reduced function. Now it'll take an x of 1. So we plug in 1 over 1 plus 1, and we get 1/2, which is the same as your 0.5. Isn't this the same as 0.5? So here's our removable point of discontinuity. So in this function, as x approaches 1, its value would be 0.5. Okay. Now this next one's a little bit tougher. When we have to rationalize. We have a couple of domain restrictions. We have one with the radical, which we're not going to address, but we have the other one with the denominator. So the denominator says, I can't use x is equal to 0. So we want to know, can we somehow eliminate this point of discontinuity, or is it a jump discontinuity, or what happens? So when you graphed it last night, again you saw, what would this value be? 0.5. So we know we've got a removable point of discontinuity. Now in the past, when you had something like this, and you had to simplify that, what did you multiply that by? To get rid of your radical in the denominator. Remember doing this? Radical 3 plus 5. You multiplied by its conjugate so that you can get rid of the radical in the denominator. Well, where's your radical this time? Your numerator. So we're going to rationalize by multiplying by its conjugate. And yeah, you're probably saying, so what good is that if it's the denominator I'm worried about? Hang in there. It'll happen. So when we make a conjugate, we use your perfect squares with the opposite sign in the middle, top and bottom. When we multiply perfect squares, we multiply the first term. A radical times itself pops right out. A positive times a negative, negative. And your 1 times 1, 1. Now, for the time being, don't distribute the denominator. Just slide it over. Your goal is to eliminate this x. So I don't want to mix it up into this mess. I want to keep it in the front of it. Don't distribute it. You'll just have to factor it back out. So I notice that my 1's come out. And what else now can I reduce? The x's. So I'm left with 1 over, and it's okay for us to have a radical in our denominator. Our goal was to eliminate this x, so I could see now, if I plug a 0 in there, what my point will be. So I take this, and I set x equal to 0, and I plug it in. And I get 0 plus 1 plus 1, which also gives me 1/2. So my point of discontinuity, my removable point, will be 0, 1/2. which again, when you graph this, was exactly what you saw on your table, right? Okay, let's hit another possible one. This is your old favorite complex fraction. Now again, the denominator says I can't have an x of 0 in here. I want to see, and we have another one, but right now we're just going to worry about the limit as it approaches 0. That's the guy we want to address. So we have one here, but we'll approach just this one. So we need to eliminate that. So we need to resolve this complex fraction. Again, when you graph it, graphically, you'll see where your point is. What point should that converge at? What should be its y value? 0.04, right? 0.04? That's where it should converge at. So now, let's reduce your complex fractions. Find your common denominator. What factor do I need in the numerator? What factors do I need? I need, let's put this over 1. I need this guy. And a 5. Good. So, in the numerator of every term, multiply by your common denominator. And reduce this. You should crunch down that fraction. Out comes your 5 minus x. We have 1 times 5. Out comes your 5, and be careful of this, keep it in parentheses. We have 5 minus x. In your denominator, there's a 1 on the bottom, so you're going to multiply your 5 times x times 5 minus x. Leave everything, don't distribute yet. Resolve your numerator. This will give you negative 5 plus x. What can we take out? If we combine your 5 and your negative 5. Good, out. We're left with x over 5x. Can we reduce anything? Yeah. What about the x's? X's? 1. So now we're all the way reduced. Now, I'm not going to have a problem when I plug 0 in there. So I'm going to plug my 0 in for x. And I'm going to find my corresponding y value. And isn't this the same as 0.04? Wasn't that the point we found graphically? Now we found it algebraically. So we evaluated this limit. So as x approaches 0, it would approach the point of 0.04 for its y value. That's the value of that limit. Okay. Now, sometimes we can do this from a graph, or you can do this algebraically as well. This is missing. It should say, find me the limit as x approaches 1. Because it's the 1, this is your piecewise function. And if you remember back to piecewise, we did this. We labeled this 1, 2. We said, okay, take this. For equation 1, I want to go a couple of negatives, and then my 1. Close the circle. This was 2. We want to start at 1, go a couple up, open the circle. Now, here's the deal. If, because they're using the 1, if this one and this one is the same, then they'll overlap. They'll be the same point. If they don't, we're going to get this jump. So we plug in your 1, and all you really have to do is plug your 1 in. To graph it, though, pick a couple of points, graph this part of it. Close it there. Pick a couple of points, graph this part of it. It's the ones that matter. So if I plug a 1 into this one, I get 4 minus 1, I get 3. If I plug a 1 in here, I get 3 minus 1, I get 2. These are not the same points. So graphically, you can see the jump, and algebraically, you can see that they're not the same point. So this does not have a limit. The limit does not exist. It doesn't converge at the same point.